number 901, whatever was up there. The server will see what records it needs to return. It doesn't know it's looking for a social security number, and it doesn't know the value of that number it's looking for. So let's look closer at how it does this. So you get a query from the encrypted client. You can see that social security number is in the clear. It hits the driver says, hey, this is an encrypted field. It goes up, gets a key from the customer provision key provider, so that can be the AWS KMS, it can be GCP's Cloud KMS, Azure's Key Vault, a KMIP enabled client, and it brings that back down, it does the encryption, and it sends it over to the database. You can see that in that encrypted search key that it sends over. That's part of the magic that we'll talk about later. So now it hits the database does the processing on that data, and as you can see, that social security number is fully randomly encrypted. That social security number in every document is a different ciphertext. So this isn't deterministic encryption where every time it's encrypted to the same ciphertext, a different ciphertext every time. And then it returns that data to the driver, decrypts it, and the application gets it in the clear. So the encrypted fields, again, are always encrypted, stored, transmitted, processed, and retrieved as ciphertext. That data is ever only plain text in your application. So use cases. There are a number of them. Say financial services, you need to find transactions based on a range of dates, or you're doing some fraud investigation, you need to find transactions with a number of dollar amounts. Or human resources. And you need to find your employees, but need to look at those last 4 digits, the non-sensitive parts of the social security number, to find them. But you still need to store that social security number encrypted. And in healthcare, say you've got some agents looking up a patient's number, or a patient's name, excuse me, and they don't know the full name, or it's Cynthia versus Cindy. They can actually type in the first few letters of that name and get all the results back. Making them do like an equality search on that, if you can imagine how long that would take. So I'm sitting there, how do you spell that again? Oh, let me try this again. Let me try this again. With a prefix search, they can do that on that fully encrypted data, just like they can today on the clear data. So the benefits. We just talked about. It's those rich queries on fully encrypted data. Range, prefix, suffix, substring, equality. No other solution can do those today. It's end-to-end, fully randomized encryption. Again, it is only ever decrypted when it hits your client. It is encrypted everywhere else that data travels. It is groundbreaking technology. This is something that, again, MongoDB is the only one that has, based on a field called structured encryption, but it is all standards-based cryptography. This is not an SDK that we're putting out. This is not a roll your own crypto. So this is using AES 256, HMAX, SHA-2. So this is all FIPS, NIST certified boring cryptography, as Ken calls it. Next is these are strong technical controls. So you control that key. This helps you meet things like GDPR and CCPA and PCI and the number of acronyms that are coming up every month, it seems like, from different industries and different localities that require data privacy controls. Fast app development. So again, this is a full solution that we've built out. It's not you make this call to encrypt, you make this call to HMAC, you have to do all the key management yourself. All of that is built in. And with a component that we have called the shared library, you actually don't need to change your application code at all. It will do a translation from a normal MongoDB query to an encrypted query without you needing to do anything. And lastly, it reduces institutional risk. So there are a lot of customers, especially financial services, in a lot of these kind of longer running industries, that have big concerns about moving off of their on-prem solutions to the cloud because of the control that they give away. This gets them back to that control because, again, you're controlling those keys. You control where that clear data is. So our journey and roadmap. So back in 2019, like I said, in 4.2, we developed client-side field-level encryption and put that out into the world. In 2021, MongoDB, as Mark mentioned, acquired a company named Oroki that has the pioneers in encrypted search. And from that, we spun off our advanced crypto research group, which was formed just a little bit earlier this year. Seni and Tariq are heading that, but we have a number of other PhD cryptographers onboarding to kind of move us along into these new use cases. So Queryable Encryption Preview, that's what we're announcing today. It is in preview, and we're starting out with equality searches only. Next, we will go to range, then prefix, suffix, and then substring. And the future really is taking Seni and Tariq's work and getting these new privacy-enhancing capabilities. So what is in public preview? Like I mentioned, it's equality, but it's also this crypto framework. So all the piping that we needed to build in order to bring range, in order to bring prefix, suffix, that was a year-plus effort to get us to where we are today. The equality, and also built in to Compass, the ability to support queryable encryption, so configuration, decryption. It now can act as an encrypting client, just like your application can. It also cannot act as an encrypting client if you don't want it to. So what is the public preview? So it's available with the 6.0 RC release. It is an evaluation only. There may be breaking changes we're not planning, but just keep that in mind. So it is not recommended for production workloads. When we go general availability, that's when it'll be ready for production workloads. And then post, range, like I said, prefix, suffix, and substring coming in the coming months. So, Ken, what is this magic?
All right, thanks, Cynthia. All right, so one of the fundamental questions you need to ask with any security control is, what is the security model? What are the benefits this gives me, right? One of the things I don't want you to take away from the talk today is that this is in any way a silver bullet, right? We're not saying that if you add this technology, your systems are now hacker-proof. All the sort of fundamental foundation 101, principles of building secure systems still stand, but this is an important control which for a lot of workloads, can open up a lot of interesting use cases. So the security model specifically is what we refer to as multi-snapshot secure. That means an adversary, whether they're a cloud provider, an attacker with root access on the underlying Unix box, if they're a DBA with like global cluster admin privileges, if someone has the ability to see all memory, CPU state, L1 through L3 cache, logs, this is the adversarial model. This is not meant to protect on the application side, right? The application side is the source of truth. That's where your clear text starts, and that's who holds your keys. If you have a really lousy Python server and it gets hacked, you're out of luck. This won't help you. If you have a really bad, dependency on something that's not been patched for 3 or 4 years in some middleware, this won't help you. What it's specifically designed to do is on the database side, to protect the contents of the data on the database. So what are the formal security guarantees? Some of these are pretty familiar terms with the security folks in the room. Others may be less familiar with it. One of the key points is that there are verifiably secure primitives that make up things like the document encryption, right? So we'll get into it in just a second, but there's sort of a bifurcated path. One is the fundamental protections of documents, and the other is the innovations that we bring with the encrypted search index. Even adversaries that can adaptively query an encryption oracle. Now think about this. If you're a DBA, there's only so much you can do for adaptive queries because you don't hold the key. So you can issue plain text queries, but that doesn't buy you much. you'd have to actually hold the key. And if you're holding the key, why are we attacking the database? You've already got access to it, right? The encrypted indexes have a sort of a different notion of snapshot security, and we'll get into that in just a bit as well. So the boring part, document encryption, standard authenticated AED, AES encryption. We use an encrypt and MAC authentication scheme, AES CTR with HMAC SHA 256. One of the things to keep in mind as we describe some of these things is if you were building a greenfield crypto system on a single platform with a single language, you might make some different choices. But we support like 12 different languages, every major programming language, right? So Python, Node, Java, C#, C, C++. We run on embedded systems. We run on ARM. We run on x86. We run on IBM Z-series mainframes, and on every operating system you can imagine. So the choices that we make are very conservative and sort of very standard. These are well-known primitives that are well understood and well characterized through a decade plus of cryptanalysis. At the top level, there's a 96-byte composite user key that comprises 3 different subkeys that are used for the capability. So AES-CTR is used to encrypt the document itself. Because it's an authenticated encryption scheme, a keyed secret HMAC is used to provide that authentication, and then an additional 256-bit key is used for the encrypted search operations. So the innovation, so that was all sort of standard, familiar things, hopefully to the security nerds in the room. What is innovative here is the functional search index, and that's really what we're introducing here. It's based on a novel structured encryption construction. Structured encryption is something that's been sort of developed in the academic crypto world for 10, 15 plus years. It's not seen sort of industry take-up for a whole lot of reasons. One of them is things like maintaining state, right? So if you have a single application server talking to a single database, your world's pretty straightforward. If you've got a huge distributed database with sharding, replication, you've got multiple clients. Some of them have, flaky network connections. Clients die. Things come back to life. You don't want to have to put the burden on the developer to get into distributed caching and things like that. It's hard enough to write like a secure, web app today. We didn't want to, sort of complicate things as well. So what it does, though, and one of the innovative things is it provides a statelessness. The database maintains state, but it's blind to the state that's maintaining, right? This is highly available. We built in sharding support, from the beginning, really critical for, bigger workloads. One of the key data structures is something called an encrypted multi-map. Basically, think of it as a type of reverse or inverted index with encrypted labeled list pairs. We use pseudo-random function evaluations. In this case, when we say PRFs, we're referring to keyed HMACs. And so it makes for really fast, efficient EMM lookups. And then again, just to remember, HMACs are secret keyed digester tags. The database never has access to that key. In terms of some of the comparisons, so client-side field-level encryption, it's not being deprecated. We've got some big global financial customers that are using this in production today. Actually, let me spend a second to talk about that because I really want to kind of underscore this point. Some of the biggest banks in the world are using this. And I don't mean for like an analytic workload or some marketing website. I'm talking about core transaction systems, core operational data stores. We have customers that are moving 2/3 of the world's money around on this platform. We have customers that are doing encrypting entire national pension systems. Every infant, child, mom, dad, working age person, and pensioner in the country, their medical data, their financial data are using some of this core technology. And it's those sort of security critical workload customers that have come back to us and said, we love the capability, but we need to be able to do more expressive queries. We need to be able to do things like range searches and search for strings and things. And in the past, our answer had been, that's really hard. That's a really tough engineering challenge. And while there's been some promising work in the academic world, it hadn't really been possible. It's through our collaboration with this research group at Oroki Systems that gave rise to the acquisition that we made, and eventually to the formation of our advanced crypto research group headed up by Sunny Kumar and Tariq Moatz. And so we're super excited about that. I think by this summer, we should have something like 7 PhD cryptographers in-house. So this is a serious strategic investment in sort of usable security. Queryable encryption is probably best suited for net new systems. If you've got existing workloads with certain document shapes and things, if you've got really heavy write workloads, it may not be the best suited. It's really designed for really fast search. So some other comparisons, both work on confidentiality and integrity as an end-to-end solution. There's both queryable and non-queryable options. Authenticated AES, all the key management features that you've come to understand with Mongo. And actually, we're expanding these in the next, I think, month or two, right? So it didn't get a lot of coverage, but we're super excited about this. If you have an on-prem HSM where your keys are held, you can now migrate that to KMS, to Amazon, to Google, to Azure. You can swap cloud providers. You can move from cloud back to on-prem. You can move from HashiCorp Vault to a local key to HSM. Obviously, you have to be authenticated, have the right permissions, et cetera. But it opens up a lot of really interesting flexibility that doesn't tie you into a particular platform. So that's a really cool feature. Encrypted data, it's stored as, in the database as bin data. So from your migration perspective, your backup tools and things like that, they'll just work, right? Even if you've got legacy integration, if you need to move data around from the tools perspective, this is just standard bin data in MongoDB. It doesn't know any different. One of the things we are also doing, which I think there's going to be a lot of DBAs that sort of celebrate this, is we're getting rid of MongoCryptD. MongoCryptD was a piece that we ran as a long-running daemon, and what that does is the automatic parsing and query translation. The feedback we got was kind of a pain to maintain. We have to, deal with it with containers and boot time, startup, et cetera. We have to sort of follow it and so forth. So we're just eliminating that. So now going forward in all the both client-side field-level encryption as well as the queryable encryption drivers that support it, you can use either MongoCryptD or this new shared library. A couple other comparisons. So with CSFLE, 99.9% of the logic was client-side. The server was basically unaware of what was going on. And you could do equality matches. We didn't really introduce any additional data elements. If you had a field called SSN, that's what you got. If you wanted to search it, it was deterministic encryption. If you wanted to use randomized encryption, you could do that, but you either have to query on like by reference with some other field, or Cynthia mentioned in the earlier part of the talk, you'd have to bring all those documents back client side, which can be kind of prohibitive. With queryable encryption, it's a different security model. It's really limited snapshot or a really strong snapshot security model, very limited leakage, even on low entry fields. So things like state code, diagnostic code, gender, things that are low cardinality that have very few values in larger systems, those pose a challenge because developers would have to think about, well, what's the shape of my data likely to be? With CSFLE, we could say things like, if you're storing a credit card number or a social security number, you're probably fine. You're probably not too worried about something like a frequency analysis attack. But the point is that you'd have to think about it as a developer. You may not know the shape of your data. You may not know how that's going to look. And so those considerations just go away now. It's specifically meant for all types of data, but including low entropy field data. And as we said, we're rolling out range, prefix, suffix, and substring in the months ahead. This, what we're introducing in 6.0 is kind of the foundation, the core cryptography framework that lets us do this. We did add some additional data structures, so there's something called sake content, and there's some additional metadata collections that get created for those encrypted fields. Eventually, we're going to make it so that you don't even see those at all. They're just invisible. They're already kind of invisible to tools like Compass and so forth. But as the product evolves, we'll just eliminate those so they're not even seen. It's sort of like a hazmat zone. And because if you do touch it, it's not a good time. So the trade-offs. FLE is great for really flat, wide histogram type data, right? If you need to do search and you've got lots and lots of cardinality, it's a great solution. It does, depending on whether you're using deterministic or encrypted mode, have some frequency leakage. The storage overhead is minimal. It's a few percent, really, unless you're storing like pure integers, in which case it gets a little more excessive. With queryable encryption, there is going to be a storage overhead. The customers that we've talked to tend not to be too sensitive on storage. The finds are really fast. So in some of our profiling techniques and tools that we're using on multi-million record data sets, I couldn't really do good profiling because the results were coming back like sub-millisecond. So really good performance in terms of search speed. Inserts are a different story. So if you've got giant batch jobs that are doing hundreds of thousands or millions of inserts at a time, it may not be super well suited. If you've got sort of a 95% read to 5% write or update, that's probably the sweet spot. How's this different from some other things out there? So Queryable Encryption, again, uses at this foundation structure encryption. It's ideal for a general purpose database, the kind of things that our customers are looking for. It's software implemented. It doesn't require special hardware. It's hardware agnostic. It doesn't require secure enclaves or hardware enclaves or anything like that. And it's optimized for sublinear search, which means that as your size of your data records grows, it's not a linear progression in terms of delay for search results to come back. We have been asked quite a few times from customers, is this homomorphic encryption? It's not homomorphic. It shares some, at a very superficial level, some similar characteristics in the sense that the database is blind. This trusted third party doesn't see operations. But homomorphic is really meant for things like arithmetic operations, right? I need to run descriptive statistics to get means and totals and things on financial values. It's not really suited for search, and one of the reasons is it's not sublinear. It's at best superlinear, and it can get really computationally, a really high computational overhead over time. Secure enclaves, again, those have a role. We're actually even partnering with some companies that are doing some innovative work in that area, but it's a different security model because inside those secure enclaves, there's clear text, and that may not be, something that your risk tolerance, sort of allows. But in any event, this is not relying on any kind of proprietary hardware. How can I try it out? So the components and licensing, let's get into that. The core crypto is open. Actually, I'd say probably 90% of this is already on GitHub if you know where to look. It's supported in Atlas, Enterprise Advanced, and Community. We're big believers in no black box and sort of open standards. We really encourage the security community, the crypto community, to give us feedback, to review it, to do the cryptanalysis. We're also having some parallel efforts done, which we'll have some more to say about that soon in terms of sort of independent review, and we can share that with you shortly. With automatic encryption, that's an Atlas or Enterprise Advanced feature only. This shared library called QuickShared is available now for evaluation. Again, it enables encryption without significant app changes. It keeps developers from shooting themselves in the foot. This shared library package is on the Enterprise Downloads page. What's needed to use it? 6.0 server. So right now, I think we're at RC7 on Atlas, and I believe we're looking to GA very shortly, the 6.0 server. This slide is out of date as of yesterday, so we had Python dropping. My understanding is that C# and PHP are coming this week as well, and then early part of next week, we should have Ruby and additional ones to follow. The Java driver will quickly give rise to the async driver and Scala as well. So I think within the next few weeks, we should have 90% of our major drivers supported. Again, the automatic encryption, that's an Atlas feature, but we are making the core crypto framework available to the community edition as well. You want to cover the key management pieces?
Sure. Yeah. So as Ken said, coming soon, key rotation. So right now, if you There you go. Right now, if you rotate your keys in your AWS KMS, that means any keys that are created after that are protected by that new AWS KMS key, but the existing keys are still protected by your old key. With this, we give you the ability to rotate your entire MongoDB key vault with a single API. I already said that part. And it's seamless, so there's no impact to your application running. You can do full key rotation, and your application still runs as it did before. The next one is key migration. Ken touched on that. So that's the ability to change the key provider from one to another. So a single API call, again, seamlessly, you can go between AWS and GCP, for example, or a local key to Azure, or GCP to KMIP. With no impact to your application running or your data. And then lastly, the custom key management is we actually allow you, in some use cases, there are regulations that require, say, a data encryption key to be produced in an HSM. You can do that and provide us the data encryption key. Like I said, generally that's the HSM generation, but there could be other use cases where somebody would want to create their own key and provide it to Queryable Encryption or client-side field-level encryption. So all these key management enhancements go for both products, client-side field-level encryption and Queryable Encryption. And again, that's an API. Wow. We got through it with less than a minute left. So thank you all very much.